Okay, let's have a look at some exam questions. So have a read through these 3 questions, pause the video, give yourself, I would say, 15 minutes, maybe 25 minutes, something like that. Try your best, and then when you want to check your answers, press play and have a look at the solutions. Here we go. Right, the first question I would say is quite a standard question. So we have plain polarized light. So that means the light has already been through one filter, one Polaroid filter, so it's only vibrating in one plane. Let's assume that's vertical. It doesn't have to be vertical. And then it passes through another polarizing filter, which is, we assume it is originally aligned. So when they're aligned at 0 degrees, then we have no effect on the light intensity. So if you imagine these are vertical vibrations, they pass through the second one, and there's no change at all. So as we start to rotate that, we can imagine the other extreme, which is the second filter, which is horizontal. So if we have a vertical filter for the first one, and then horizontal, that's halfway around at 180, then no light will get through. So we're going to have 0 light intensity. And then when it continues on its journey, it will go back to its original position where we have maximum light intensity. So we need to realize, well, how does it vary between maximum and minimum? 0, then back to maximum. And this will be a sinusoidal relationship. Now there is actually a way of calculating this in terms of the angle. This is referred to as Malice's law. Most exam boards don't have that. It is possible to calculate it, and when you see it, it is a sinusoidal relationship. So all we need to know for this question is it varies in a sinusoidal relationship. So this is going to be a cosine relationship. So the way you draw this needs to represent, judged by eye, a cos curve as shown. Okay, question 2. This is another pretty standard question. I wouldn't say this is necessarily an A star. It's quite a standard one. It doesn't make it easy. So this first part A, we did have a look in the previous lesson about open tubes, and we did look at how standing waves are created in different harmonics. So the thing to remember is it's an open tube, which means it's open at one end but closed at the other end. So where it's closed, then the particles are restricted. It's very difficult for them to vibrate, so we assume that there's a node at the closed end. But at the open end, there is no restriction on the movement, so that is going to be an antinode. So our first harmonic is going to be between a node and an antinode, and we can see that that's half a loop, and we know we have 2 loops in a full wave, so that represents lambda over 4. The next harmonic, well, it's not going to be a node, that's not going to work, so we need the next antinode. So node, antinode, node, antinode. We can see that we have 1.5 loops here, which is 3/4 of a wavelength, 3 lambda over 4. So we don't need to mark on L1 and L2 in this case. So 3 marks, fairly typical question. Draw the standing wave in different harmonics, mark on the nodes and the antinodes, and indicates the length of the wave. So that's quite a standard question. Part B is the calculation that goes with this. So it says the height of the columns is going to be L1 is 22.5 and L2 is 66.3. Now we did mention as the antinode is slightly above the open end of the tube because we have what's called C, a correction factor. Now we don't actually have to worry about this. If we just compare these two and subtract one from the other, then the correction factor actually disappears. So we could include it in the algebra, but we don't actually need to. So we can see that approximately, ignoring the correction factor, then L1 is lambda over 4, and L2 is 3/4 lambda. So the difference between the two, so 66.3 take away 22.5, is going to be the difference between these two fractions, which is half, and we want the full wavelength. So if you work out the difference between the two and then multiply by 2, that will give you the full wavelength involved in this case. We're told the speed of sound is 340, so V equals F times lambda. Make F the subject. We have 340 over your previous answer, and we get an answer of 388. Okay, question 3. So I would say this is a more difficult question, an A star question. I think there's several reasons why it's more difficult. It obviously requires a deeper understanding, but the main thing is they've given this formula. Now this formula is not on the specification, or most specifications. It may be on the one that you're studying. But this is sometimes what they do in the exam. They will give you a formula that you have not seen before. Now, if you've done lots and lots of exam practice and read the textbook from cover to cover and looked at as many examples as possible, then you may have come across this, but not necessarily. This is why it's difficult. They're saying, here's some new information. Can you work with it? And that's really quite intimidating. So you have to take a deep breath and be confident to have a go. So let's have a look. We've got a relationship to find the frequency. Well, that's what we're trying to do here. That's equal to 1 over lambda, so we'll need to work that out, multiplied by the square root of t over mu. Well, we're given t and we're given mu. So this is effectively a substitution, but it does require a little bit of thinking because we're told that it's vibrating in its third harmonic. So we need to think, okay, well, 3 loops means the third harmonic. 3 loops is 1.5 waves in the length of 1.2 meters. So the wavelength is 1.2 divided by 1.5 waves, which is 0.8. So that's our first calculation, and that might have thrown some students. Once we've got that, it's a relatively simple substitution, and we get our answer for part A, which is 216.5. Okay, part B. So we increase the frequency, and then resonance occurs at a frequency of 361. Now, this is a potential confusion here. It doesn't say the next resonance event, it just say that resonance occurs. So it could be the next one, it could be the 4th harmonic, it could be the 5th or the 6th or the 7th, we don't know. And it says which harmonic mode is associated. So we're trying to find, which harmonic mode is associated with this frequency. So what we can do is rearrange this formula to make lambda the subject, because in this case we're given the frequency. So the t over mu is the same as before, and we get lambda as 0.48. So you'd get 1 or maybe 2 marks for that, possibly just 1 mark for that. And then we need to think, well, what do we do with that if the lambda is 0.48? So we need to work out, well, how many waves does that represent? So similar to what we did before, the length of the string hasn't changed, that's 1.2. If the wavelength is 0.48, then I can divide the length of the string by the wavelength, and I get 2.5. So I've got 2.5 waves on the string now, as opposed to 1.5 before. And if it's 2.5 waves, well, we know that 1 wave is 2 loops, so 2.5 will be 5 loops. So that would be its 5th harmonic. Okay, well done everyone. That is the exam questions for polarization and standing waves.